So we're going to look at the kind of particles that are involved with radiochemical reactions. I've got an example here of a nucleus, and this just represents a random nucleus. It doesn't even necessarily have to represent a real nucleus, but what it should represent is a nucleus that feels that it's unstable for whatever the reason. When a nucleus feels like it has too many neutrons, what it can do is it can go into those neutrons and it can actually convert a neutron into a proton. Is that not craziness? In the process of converting a neutron to a proton, you're actually changing what the element is. And when it does that, it's going to release the energy. So there's like going to be, if it's unstable, then there's going to be like extra energy flowing around trying to solve the problem. So in fixing the situation of the neutron to proton ratio, we'll be releasing energy because it doesn't need that extra energy that was a result of the incorrect ratio. And it's also could leave a particle. So the particle, something like this is a beta particle. We're going to look at those beta particles. But again, like if this were 2040 calcium, it's going to be releasing energy. It's going to be releasing a particle, and it's going to be changing what it is. So as we look in here, these are the different kind of particles we'll look at. So there are some natural decay reactions that just naturally happen, and they involve these three particles. And this is a huge amount of energy. It's more than an X-ray. So this can be released with any of these, and you can also release energy that's much less energetic than that one. We also, over the side, have got examples showing you what to expect of what can actually stop and what the radiation can cause and what it can stop, what can stop it. So before we knew what these were, we just called these using the Greek letters alpha, beta, and this was actually originally considered a type of a beta particle also, until they figured out that one of them was positive and one was negative. It's still called a beta particle, and yes, there is an E there. This is not a proton. This is a positron. Is that not crazy? We're suddenly introducing some new particles to you. Go ahead and Google positrons if you want to learn more about them. We're just letting you know that it releases a positron. So these are more natural kinds of decays, and you should know that this right here is helium, and it's very slow moving compared to the other ones, because you can even see, like, imagine size-wise, you can see this is a lot larger. So it might be able to do a bit of damage, but it just can't move very far and go very deep. So this can be stopped by paper, which is way thinner than your skin. Your skin can stop it, like, no problem at all. But paper, is fine for stopping it, and paper's very thin. When you're looking at these beta particles, like I said, skin can stop them. And what this beta particle is, it's like an electron or a positron. And they are basically high energy, because when they come off the atom, they're leaving at a speed. And this particle has the same mass of an electron, but it has a positive charge. So again, it's not a proton. Protons are like 4,000 or 1,000 times heavier. But both of these are different types of emissions. Now, note, if you were to breathe in something that has alpha or beta radiation, that's a kind of a different ballgame, because your lungs are not like skin, right? They're like less than paper in a lot of cases, and you have got to keep them protected. So if you breathe in a chemical that releases, or an element that releases alpha or beta radiation, your lungs can be damaged by that. But if it's a solid that's radiating, then it's not even going to get to your lungs. I mean, not even if you eat it, that's going to your stomach, right? So just keep that all in mind when you're dealing with radiation. These types right here that are naturally occurring, these are not the ones that cause the big issues. I also like to mention that even though we have particles that can cause some kind of damage, they also can be used medicinally in really great ways, like alpha particles, beta particles. If they are implanted in the middle of a large tumor and sealed up in the tumor, then what they can do is just irradiate and kill the tumor and not affect you at all. So they can do really great things, also. So everything has its source of balance. Also note that you can have protons coming off, you can have neutrons coming off, you can have gammas coming off. You can also, in the case of these two, throw these at atoms. It's called bombardment, and then make the atoms fall apart. So those are different things that can happen with radioactive particles. One last little tiny detail. These top numbers right here, this is the number of protons and neutrons. This is the number of protons. If we skip past the weird beta ones, again, this all still follows because this is protons plus neutrons. A hydrogen doesn't have any neutrons. Meant for that to be up there. If a hydrogen doesn't have any neutrons, then that's why there's a 1, because it's 1 proton and 1 neutron. And I've just lost my page. There we go. There we go. And then finally, a neutron does not have any protons, but it does have a neutron, so protons plus neutrons is 1. This would be 0, 0. And then this one right here, these guys are kind of weird. We are actually indicating their charge, and because electrons are so small compared to the other atoms, you know, a factor of 1,000 difference, we just go ahead and say that these have 0 mass comparatively. It's really important to write them like this, though, because when they go in chemical reactions, you'll see what we're going to do. It makes it way easier to figure out what the products are going to be. Final note, these ones might be with a beta or not, and this one could be called negatron rather than beta, but these are both beta types of decays.